With a growing global population increasing the demand for food consumption, it is critical to ensure food remains safe and healthy while en route from production to consumption. Data-driven insights into food quality characteristics during transportation have helped ensure the food remains of good quality while being transported, keeping food loss and waste during transportation at a minimum. With this in mind, Group E has proposed a solution towards clean growth in the Industrial Strategy Challenge Fund. The solution is called the Food Quality Sensor. This is a device that will be installed into commercial food transportation vehicles, measuring different attributes that contribute towards food quality. Various products require the maintenance of varying temperatures, humidity, light intensity, and alcohol levels to ensure that the product is of satisfactory standard. Our product will check whether the attributes are maintained within a certain threshold. These thresholds can be predefined through a supporting phone app. As well as the phone app, there is also a web app for data analytics. These supporting apps will be further discussed later on in the presentation. The team was split into hardware, software, integration, and financial. As seen here, these are the individuals in each team. I will now hand it over to Sarajan, who will go over the hardware overview.
The goal for the hardware team was to create a device which could measure environmental factors which influenced food to maintain its quality when transported. I will give you a brief description of what we came up with. We use an Arduino Every to control and take inputs from all our hardware. As you can see from the diagram on screen, we chose an MQ3 sensor, DHT22, and BH1750 light intensity sensor to measure the environment of transport. Once we had our sensors, we had to provide a way to power them as well as the rest of the circuit. We decided to use a battery that passed through a buck converter. To view the sensors data, we created an LCD interface as well as transmitting data via Bluetooth Low Energy to a phone. We used a push button so the LCD will only stay for 2 minutes as to preserve battery life. Once all the hardware was tested and worked, we made a 3D printed box to house the components. On screen, you will see a schematic of the final design we came up with. Now that the overview is out of the way, I will talk about the power management system. The battery is connected to a rocker switch, so the device can only be powered when it's needed. The Arduino receives the full 9 volts, whereas the rest of the devices can only receive 5 volts. To achieve this, we used a 5 volt DC to DC buck converter. Now Alex will talk to you about sensors.
Thank you, Sharajan. So as mentioned on the slide before, we use 3 sensors in our product: the DHT22, the BH1750, and the MQ3. These are used to monitor 4 variables on the transport of our produce, these being temperature, humidity, light, and alcohol emission. Starting with light, the BH1750 is the digital light sensor that we use when considering photosensitive produce. It consists of a photodiode that communicates through the I2C protocol back to our microcontroller, being the Arduino. The other 2 environmental factors for food storage, being temperature and humidity, are handled by the DHT22 sensor. The temperature is measured through a thermistor, and the humidity via 2 electrodes with moisture holding substrate between them. Ions are released by the substrates, and as the water vapour absorbs them, the conductivity increases between the electrodes, changing the resistance, which gives us our humidity value reading. Our last and most unique sensor is the MQ3, which is a metal oxide semiconductor that works as a chemiresistor. It is used to sense the alcohol concentration by calculating a change in resistance of the material when exposed to alcohol, which I'm sure you can appreciate is useful, as certain fruits can produce alcohol when conditions degrade and they begin to rot. Thank you for your time. I'll now pass you over to my colleague.
Thank you, Alex. I'm now going to speak about the progression of our design from the original schematic to the final PCB design we used in our actual product. The first step was to create our initial variable design. We used this design as a way of seeing how all the components would interface together and seeing how much space we actually had. The problem we ran into was that the software we were using, Fritzing, did not have all the sensors that we needed, and also the fact the light intensity module we were going to use, we decided to change just after this design. This design is also boxless, meaning the button is on the actual Arduino. In our follow-up wearable design, it wasn't actually made in the lab physically as our wearable 1 design was, but it was very influential in our final PCB design, as it is where we came up with this design where the Arduino sat in the middle of the design and the components surrounded it, meaning we had to do the least amount of routing. We then moved on to the final PCB design. This design was very easy to do, as we used the same software that we used for the wearable design, which was Fritzing, and it allowed us to directly translate all the pin connections. To also make it easier, we made a pin connections table, as you can see on the slide on the far right. The only problem that we came up with in the PCB design was the fact that the software only allowed for 2 layers for the routing, above and below. This meant we had to be very smart with the way we routed the product, but as you can see in the final PCB design on this slide, we use very little routing and the product is very compact, adhering to our design brief. All the components are close together, but not too close to cause safety hazard when soldering the components, and it created a very sleek design that fit perfectly into the box. I am now going to pass it over to my colleague Tom, who will actually speak about this casing. Thank you.
In order to create the casing for the product, we elected to use the Fusion 360 Design Suite, as its full capability to design and render the product all in one application made it easier to create a sophisticated yet functional design. To begin with, the box was created and the required holes were extruded for the components. Said holes used measurements based off of the real components that had been ordered in prior. This left a nice framework that can be seen in the video, which could then have the components added one by one. The addition of the components was completed by a mixture of methods. Most components could be obtained pre-constructed as renders from GrabCAD, a free OpenCAD design library. These could then easily be inserted into the design for usage. Any components that weren't present here were then created separately within Fusion. Once all the component models were present, it was then onto the matter of inserting all the components within the box to test for fit. To make sure there was no component overlap, specific non-overlap rules were used on a per component basis. This meant if there was insufficient space for a component to be placed, Fusion would raise an exception, allowing action to be taken accordingly. Finally, the case was then rendered into a realistic environment using Fusion's real-time renderer. This created the final renders for our design, which was then used to create the finished box. Over to James for details on hardware and software integration.
The food sensor has been designed to work in conjunction with a mobile phone app. It integrates with the phone through Bluetooth Low Energy. This mode of communication was chosen over classic Bluetooth because of its optimized low power consumption, something that is critical for food deliveries lasting several hours. The driver connects with the food sensor through the app, which only registers for updates to sensor values. This means the food sensor sends out short timely bursts to the phone only when a sensor value changes. The phone app checks for an active status every 5 minutes and attempts to reconnect if a connection is broken. The phone sends out these values every 5 minutes to a real-time database powered by Google Firebase. This database is highly scalable and can serve thousands of drivers sending information simultaneously. Now my colleague will elaborate on the design of the mobile app user interface.
Thank you, James. Hi, I'm Shamir, and I was in charge of the phone app. The main purpose of the app is to allow the driver to set food types that they are delivering and be able to calculate a threshold that will allow the food to be safely transported. Now, the values coming in from the Arduino would be then compared to the thresholds, and if any exceeded these thresholds, a notification would be sent to the driver. The app was connected through Bluetooth with the Arduino, and the data would come in, and then it will be displayed. So the 4 different values that we're reading will be displayed on the dashboard in the app. From the dashboard as well, we were able to send data straight to Firebase as well. When designing the mobile app, there's a few design considerations that I had to take into account. The first was that the UI should be suitable for someone who's driving, so it should be simple and not distracting, but also show valid information. Another was that we needed a secure login. This works in hand with the web app, but each driver will have their own specific login. To allow the driver's phone to connect to the Arduino or the sensor in the back of their vehicle, we needed an interface to allow them to connect to the Bluetooth. A dashboard was needed for all the readings that were coming in from the Arduino, so all the values, all the 4 different values that we're reading in would then be displayed on the dashboard. If any of these values exceed the thresholds, then a notification alert can be sent to the driver. To set the thresholds, initially we needed the driver to pick his different food types, so there needed to be an interface for that as well. Overall, the development was done on Codula, which was a free-to-use online Android app development tool. It was simple and had good integration, as it had all the components that we needed, such as Firebase and Bluetooth. So the login screen looked like this. It's quite simple. The driver just needs to put the details and you can go into the next interface. This is the next interface where you're presented with 3 tabs: the dashboard, device calibration, and settings. The dashboard shows all the 4 readings that are coming in from the Arduino. The device calibration allows you to connect to the device through Bluetooth and set your food types and thresholds. The settings, you can access settings such as account and notifications. I'll now hand over to Tom, who will go over the web app.
Thank you, Shamir. As mentioned, it was my responsibility to create a browser-based web application. To do this, I decided to use Ruby on Rails, a web application framework that utilizes the Model View Controller architecture to create an intuitive and powerful application. The primary focus of this application was to introduce individual account control, whereby admins can log into their own secured account and manage the incoming data as they please. To achieve this, techniques including utilizations of gems such as Devise were implemented throughout the app. When combined with my own bespoke code, the creation of the app you're about to see was yielded. To begin with, Devise is being used to create a secure login page for the user, whereby they can enter their credentials to log into their personalized dashboard. Alternatively, if they do not yet have an account, they can sign up using the provided sign-up page, as shown here. If the user forgets their password, they can simply click on the Forgot Password link, which will instruct them to reset their password via an emailed link. Once signed in, the user can then navigate to the App Synchronization tab, whereby they can then view the integrated live data feed from all of their different drivers. Alternatively, if they wish to plan for a future additional transport, data can be entered manually into an SQL database, which is saved for later viewing and editing. The process of this simple form can be seen here. To help support our clients, a contact page has also been provided. This page allows for the creation of contact requests using the provided form, as well as storing previous contact history for later viewing. If the problem is resolved, the client can delete the request or choose to keep it for their records. Finally, full account management is provided, such that the client can change their password and details as they wish. The client can also delete their account with us here if they are unsatisfied with our service. I will now hand over to James, who will explain the integration between the phone application and the web application.
To complement the web app, a dashboard was designed for data analysis to convey meaning and expose insights into the data through trends, outliers, and data patterns. The dashboard takes data from a real-time database and NoSQL database, which leverages Google's world-class hardware to store and sync data. The phone and web apps communicate with the database in real time, such that data can be generated, uploaded, and visualized instantly. The database utilizes a local cache on driver devices to store changes when offline, then synchronize them when the device goes online. This way, no data is lost. The dashboard, secured within the main web app, was built from scratch, using powerful Python libraries like Pandas and NumPy, capable of fast data analysis and manipulation. These, coupled with Plotly, data can be visualized in form of real-time charts and gauges. The dashboard is fully responsive for any choice of devices, be it desktop or mobile. A user, part of the monitoring team, can view the data in a compact form with several filters available for different drivers, sensor data type, and date ranges to sift through the data and quickly highlight points of interest. Hovering over the plot reveals individual data tips in time. A backup solution has also been implemented to enable download of an Excel sheet containing specific drivers' information for archiving. The gauges show the latest sensor values for the selected drivers with clear markers of safe, tolerable, and danger ranges. These values are checked against safe ranges for the food in transit. If any of these values go out of range, this value is logged and an SMS notification is sent out to the driver for remedial action. I shall now hand over to my colleague for a discussion on the finances of the product.
Thank you, James, for the explanation addressing the integration of the web app. It was my role to look into the business side of things and to project future financial forecasts, and in order to determine whether we would generate enough profit to survive as a company over a period of 2 or more years. I went about this by taking a deep dive into the financial statements of the company, looking at the income statements, the balance sheets, and future cash flows, while also taking into account the initial costs incurred, such as the overhead. Also to be included would be the manufacturing unit costs, the utilities, the income and corporation tax, the debt to equity ratio, and how we would go about increasing market share throughout the years. In the end, me and Sharajan came up with the idea of having 3 tiers, which clients could subscribe to, all with varying prices and each tier specifically catering to the client's needs, which allows them more than triple our profits over a period of 2 years. It was also my responsibility to look into the sustainability aspects of the food quality sensor and to look at what the potential benefits would be. One of them, would be that with less food being wasted and the food being kept at the correct temperature, there'll be less of a need for unnecessary trips. And so with trucks drive with less wasted trips, there'll be less CO2 emissions being released into the atmosphere.
When delivering goods, there are always some unforeseen circumstances that can occur. For our demo, we'll be demonstrating and simulating a delivery that should be in chilled conditions, but is taken out of chilled conditions. Okay, so to set up, we first begin with the login. We use an admin account just for demonstration purposes. Once logged in, you'll be presented with the device calibration screen. So on this screen, you have it allows you to connect to the device and also allows you to set your presettings. But for the demo, we first need to connect to the Bluetooth. So we'll do this now. So in this case, it'll be the first one, as that's the name of the Arduino that we have. Once the Bluetooth is connected, you can see it gives you a status that is connected now. Now we can go into calibrating the settings. So the app allows you to select 4 different food types and you select them all here. I'll show you an example of me going through and picking a combination which is not it's not suitable to transport these together. So here I've picked fruits, vegetables, alcohol, dairy and fish. So if I try to configure this, the app will warn me saying that I shouldn't deliver these items together. So now I'll quickly show a valid combination which we can use for our demonstration. So here I've just literally picked dairy and eggs, and that's it. The other 2 options I've just blanked them out. So now if we press configure, it should be configured. Now if you go back into the dashboard, now we can see the updated thresholds. So now we can look at the last updated readings that came in. So this shows at this time these were the readings. We can now go and get a control reading where the temperature would be significantly higher than it should be and see what that shows. Once we've got a new set of readings, the warning message comes up as the temperature threshold has been exceeded. As data is being received, it's also being sent straight to the Firebase database at the same time. So the web app is now using the Firebase database for analytics. This was a simple example but gives an idea of how the app works. Overall, with our product, we help to reduce food waste and make the earth a better place in the future. Thank you for listening. Any questions are welcome.